Okay, this is part 3 on shear design. Example 9.4 is very similar to 9.3, but it actually is going to show you how to deal with the point loads. The point loads are the ones that create the drops in the shear diagram, right? That's what you're learning mechanics of solids. So really the whole issue here is not that the shear design is going to be different. It's just how to find the shear diagram, right? And so again, I mean, like before, you will just find your loads. So you had to start with your weights, right? Do your load combinations, and once you got all your loads, yeah, you find your shear diagram, and that's the key. Okay? You cannot do the shear diagram, you will not be able to design. So you need the shear diagram. And notice here the drop because of the point load, right? So it drops, and then it goes down again because of the uniform load, and then it drops again, right? And then it goes down, and then the reaction brings it back, right? The other thing that is shown here is the fact that it's giving you a bearing width, information about a bearing width, right? So what are you going to do with it, all right? So what is that one for? Right? Well, what that means is that will allow you to calculate your VU at D. Because remember, the VU at D is measured from the face of your bearing. Okay? So that's typical. Now, the other thing that you need to understand is when someone gives you a center to center dimension, this is a little bit off here, that means that you're at the center of the bearing, okay? So just to have an idea here, maybe I can draw a little bit here. No, let me insert actually. Do this, do a little rectangle. So your bearing path is kind of a little rectangle, right? So you have that, and you have that on one side, and you're going to have another one here, right? So we have those two bearing paths. So that means that the bearing paths are going to be right at the center, right? So that way. Okay? So right there is one, right? And the other bearing path is going to be here, right at the center. Right? But for the purpose of the location, right? When we model, we just use these other symbols. Remember the triangle and this roller. That's what you were taught in mechanics of solids. Okay? But in reality, what we have in other cases is bearing paths or something else. All right? They don't look like these things. These are your symbols. Okay? So as you can see here, right, the distance is measured to the center line, to the halfway of the bearing path. Right? So if I'm going to measure my distance at D, I have to measure from this face. I have to measure the distance D. So that's really the main purpose of this example, to show you how that works, okay? In there. So these are your bearing paths, okay? So that helps you understand why do we have that. So keep that in mind. So when I find then my value at the distance D, then I had to add the distance from the center line to the face of the bearing pad. Since my bearing pad is 12, then half of that will be 6 inches. And then from there, I will add my value D. So there we go, my value at the distance D from the face of the support. Okay? And so you have 6 inches plus D. And that gives you your value that you need to find at the distance D. Okay. And D. Now we are loading everything on the top like a normal beam, so you have a compression reaction, right? And our D value is given, is 29.5, right? Given here. And then we will add the 6 inches. So we need to find the shear for the purpose of designing, the value that is at 35.5 inches from the center line. Okay. And so how do we do that? We use the formula, right? So reaction at the center line minus the load, and in this case it's a uniform load, right? It's a uniform load that goes for the critical distance from the center line, so that's your 35.5 inches, right? We need to change it to feet, and so our shear then has changed from 108 to 106. Okay. So here's the diagram, right? So the distance D, this is your bearing area, so 6 inches, right? In there. And I should change this because I'm using now X's for this in all cases. Okay, so that's X. So that way it matches this, right? So RA, reaction here, minus your load times the distance X, which in this case was 35.5. Then the rest is going to be the same. Okay, so that's the only critical part. How to find my value, your design shear, what are you required to design for, and how you do measure it, okay, when you have a bearing path. And the rest, again, as I said, is the same. You find your V sub C using one of the formulas from ACI, and as we said, we're going to use only this formula for all the cases pretty much. All right. So we're going to substitute the values. Phi factor always 0.75. The 2 coefficient, there is no lightweight concrete, so this is a 1. My F prime C, it is in the radical, so we had to use in PSI, right? My B value, my D value, change to kips, and this is my value. This value right here, as long as you use this formula, happens to be half, right? So then it's 25. My BUAD is definitely way bigger than my 25, so I need to have stirrups. Okay. Next step, like all the cases, we need to find what is the length that I need to cover with these stirrups. Okay. So, do I need to have a formula? Well, let's see. We're looking at 25. So if I have my graph here, right? My graph, right? And I know, right, for my shear design, I know that this is 99 and this is 2.5, right? So there's a drop right there. So the question is, where in my diagram is the value of 25? That's as far as I need to cover with the stirrups. Well, the 25 is going to be in this line, right? So there's no need to do calculations. All I need to know is what is the distance, 14 feet. So I need to cover stirrups, right? My stirrups should cover a length of 14 feet, okay, from the center line. Okay? So that's what we have. So I know already the length I need to cover with the stirrups. So that's 14 feet from the center line, right? Because that's where the drop is. In there, right? Yeah. And so when we have that length, I mean, the rest is the same. I mean, how I'm going to find my spaces, okay? So it's 14 feet, right? So we have to cover, that's 168 inches, right? So we have then 6 inches to go to the bearing face, right? And then 162, right? To cover that, right? And so that's my length of stirrups measured from the face of the bearing. Okay? So from the face of the bearing, I need to have 162. Okay? Because everything is measured from the face of your support. Okay? All right. My required phi V sub S is my VU at D that I found, minus what the concrete can provide. So the rest had to be provided by the stirrups. So we do the subtraction, I get my number. Because most of the formulas in the ACI code are a function of V sub s and are a function of V sub s and not phi V sub s, we're going to remove the phi factor and divide by 0.75, and that gives me 75.1. Right? So this is the V sub s that we need to use. We look at the two limits that we've been doing. We are below the first limit, so that means my spacing then is d over 2 or 24, so that's 1475, so my maximum spacing is 14. By that means, this means that I cannot exceed that spacing within that distance d. Okay? I have to put my stirrups at this distance, within the distance d. Okay? You always check minimum values. Okay? Just in case. Always. Even though if you look at your table in your design aids, right? You look at your table in your design aids. So let's go to table in design aids. Right? Just to clarify that, because that's where people get confused. Right. So in the design aids, then yes, looking at your table, so we have the two columns, right? This is one column, right? And then this one right here is the other column, right? So we are here. Okay, we are here. And so what happens is that because the table, people go here and they say, oh, okay, so all I need to do is find my S values based on d over 2 and 24 inches, right? So we're here, right? So we're doing that. Yes, that is correct, but you always see these two, these S d over 2 and 24 are the same as these numbers. So I don't need to really worry about those. But I do have to check my minimum because this is required. I need to satisfy minimums. Okay, this is how, using these formulas here, is how I check that I have satisfied minimum amount of stirrups. So instead of finding the area of AV minimum, which you could, okay, I'm going to find the spacing that AV minimum needs. And then I'm going to use that as my check for AV minimum. Okay? So then you always check this equation for AV minimum that are here, because this is the only thing you have to do the checking that you're satisfying AV minimum. Okay? All right, so here is the check, and there's 30 and 28, 28.2 controls. Okay, so for minimum, you want to satisfy minimum amount, you need to provide the stirrups and no more than 28 inches. Okay? That's how you check for minimum. You're going to do 14, so 14 is a lot less than 28, so you're satisfying minimum. Okay. All right. So that means that no matter where I go, right, on this diagram, right, I can go all the way in any place here. I'm already at 14 because that's my maximum spacing, and so there is nothing I can do, right? 99.3 also exceeds phi v sub c, right? 99.3 also exceeds phi v sub c, so that number also exceeds phi v sub c. So no matter what, I'm exceeding this number, and therefore I'm controlled by S maximum. I cannot get anything less than that. So 14 is my value. Now, in terms of the spacing across the beam, we check, there are the two numbers. In this case, 24 controls, right? But because we have a width of 16, and my stirrups are going to be inside that, so that satisfies the distance of 24, right? So that 24, remember that 24 is the distance between the leg of the stirrups. Well, the leg of the stirrups cannot be more than 20 this, so you cannot be, you not even get close to 24, right? So that's easy check. So that one, you just look at it, say, okay, my cross section has a width that is way below 24, so that satisfies the requirement. Okay. Next, I'm going to find the S that I need based on my V sub S. Okay. And I find my number. Remember, this number cannot be less than the maximum, right? So in this case, it's 9. 9 is below the maximum, so we're good. Okay. And so now 9 controls over the maximum, the 14. So within the distance D, I have to start at 9 inches. Okay? I have to do that. So do I need a table? Well, I can do a little table. Okay. I can do the table by proportions. Okay. Or I can do the table by using the equations from U mechanics of solids. But again, I mean, I thought I changed all this is already, but I guess I didn't. Some of these I cannot change. Let me see. Yeah, it's picture. I cannot change those. This one? Yeah, this I can change. So we have then here X now, so all these X's. So that way we are consistent with what we're doing in other examples. So that's the only reason I'm changing it. I mean, it's not that it's wrong, it's just simply changing it to be consistent with other examples. So we do the same variable all the time. Okay. So X measure from the left side, and Z is when you do from the other end of your shear design. Okay. So we got those there, so those are easy to change. But then this one, unfortunately, is a picture. I don't know how. So that needs to be changed to X's. So don't forget, these are now X's, X, and X. Okay, because we have changed the variable to be X now. Okay. So, and I will make a change to this. I will change this one later. All right. So I find then my value. This one will change to X. Okay. So that will be X. And first thing, I start my S's, right? I need to start at 9. Okay. I could start with something lower than 8 if I want to, but not higher. Okay. So 9. I start with 9. What is my maximum? Really is 1475, but I run it down to 14. So I have 9, 10, 11, 12, 13, 14. So I just put some of those here. Okay. When my S is 9, I go to my formula here, right? I replace all the numbers. Right? And now I have my phi sub S as a function of S. So when S equals 9, I put the 9 here. That gives me my value 59. When S is 10, I put the value 10, I get 53.1. When S is 12, I put that one there. Okay? I didn't even bother to calculate 14. Okay, so I got those. Next, I'm going to add to this value the concrete part, right? And so how much was my concrete? My concrete was here, right? Giving us 50.1. So I'm going to add 50.1 to all these values. 50.1, I get that. 50.1, I get that. 50.1, I get that. So now this represents the total design shear strength that a spacing of 9 inches will give you. So a spacing of 9 inches will give you a design shear strength of 109. A spacing of 10 will give you a design shear strength of 103. A spacing of 12 will give you a shear design strength of 94.3. For the first one, you don't need to worry about that one really, because you have to start with that one no matter what. So that doesn't matter. You don't need to find the x for that. But you need to find the x's for the other values, because those are the values where you want to change to, right? So the question is where 103.2, right? Because this is the shear you're going. So this is how much you cover. So that means your VU cannot exceed this number. Okay? Your VU cannot exceed that number. That's your design philosophy, right? VU has to be less or equal than your shear design strength. So what we want then is go to the shear diagram and see where the number 103 is. Okay? So where is 103 here? Okay, in this diagram. So what is the distance x that I need to find me my value of 103? Okay. You can do it by proportions. Say, okay, this is 103 here, so I'm going to do my proportions, right? Between this value and this value, right? And that can be done. So that's the geometric issue, nada más. That's all you have to do, all right? Or, right? You can use your formulas from shear, right? From mechanics results. This is your formula. Okay? It's valid for a value of x between 0 and 14, right? And why 0, 14? Because after 14, right, your shear formula is different. You need to include the 96.8 in your shear formula, right? So it will be WUX minus 96.8, right? That's what you have there. So your shear formula changes. That's why when you took mechanics of solids, you learn how to develop moment equations, shear equations, right? But now they're here. Okay, you can use them. Okay. So as long as you are before the point load, this is your shear equation formula. So simplifies to this, and then the question is, okay, where would the value 103 happen? So when this is 103, so I put 103 here, and I solve for my x. Then in my value in feet, change it to inches. I said, okay, 96. Okay, a little more. This one, 94.3, is here at 21.9. So I said 263, but that doesn't make any sense, right? Why this value would not make sense? Two things. The formula is only valid from 0 to 14, and this is 22, right? 262 is way past the center of the beam already, right? So we're even past the center of the beam, right? So, yeah, so we're way past the center of the beam. So that means that, yeah, the value is not useful for us, okay? So that number it has to be ignored, or you want the exact number, you have to include in your formula the value of the point load. Okay? So let me put that here so you guys remember this when I make the copy available to you. To put it here. Wrong place. I have to do it here. This is not valid because it exceeds 14 feet, right? And 14 feet is the limit for that equation. So you will have to use another equation. You really want the value, you need to use a different equation, right? But you don't need that. Why you don't need that? I mean, you could, right? But you don't need that. And I'm going to show you that because we already did this, right? We already did something very similar. So why we don't? Why you don't need that? Oh, again, wait a minute. Okay. Why? Because your diagram says that you're dropping from 99 here to 2 point something, right? For 254. So where is 93? Right here at 14, right? So that's where your 93 is. So there's no need for a formula. I know 19 is here, right? So that's what it is, right? So we can add a little comment here to clarify this. No, from the shear diagram, right? No, the value of 94.3 kips, right, happens at the location of the point load. All right, so that's what it is. And so that happens there at the location of the point load. So I probably should change that. So the location of the point load, right, as measured from the center line, right, the bearing. So that's where you do everything, right? Oh. So this has moved. Yeah, because we're doing everything from the center line. Oops. So let me move that one right. All right, now it's better. Mm-hmm. So everything moved from there. So that's what we did. Or do we do it from the face? Let me make sure that we did this correct. What numbers are we using? This is 108. This one is 108, right? So 108 is this one, right? So from there, we're missing this right here, okay? On that. And so this value then would be 14. Right, 14 times 20. So that would be the value for that one. So we got then 168 inches. That's what happens. All right. But really, so what this means is that if I want to change from 9 to 10, I need to cover, using 9 inches, I have to cover at least 96 inches. And then I can change to 10 inches of space. But why would you want to change from 9 to 10? That's not a good choice, right? You want to change from 9 to 12. Or it was available to 16 or to 15, right? You want to have a jump on your spacing, right? If I have a spacing, say, of 4 inches, I want to look for a next spacing maybe of 6, or maybe even better, 8, right? So I do 4s and then 8, right? But I would not do 4 and then 5 and then 6. No, that you don't do that. Okay, you don't do that. Okay, so always look for a little bit of a jump. Okay? So in this case, the logic thing would be to go from 9 to 12 or 14, right? And all these right here, in order to do these changes, you had to cover the whole 14 feet already, right? So, and we know that's the length of stirrups anyway, right? After that, I don't have to worry about the stirrups, okay? And so, really, I'm stuck with a 9, basically. Mm-hmm. And so I had to use 9 inches. So I need to match this length that we had. So I played with that one, and I said, okay, 1 and 3 and 18 and 9 will give me exactly 165. So that covers my length of stirrup. So that means I went a little bit past my value, right? And so we got a little bit here, someplace here, from the face, right? So measure from the face, I got that. And so the next thing is I need to still cover, right? So I did that. I have satisfied my LF stirrups, right? Because I need to cover that distance. But that put me someplace here. But then I had to go from here to the center of the beam. This portion right here, I mean, it's not a scale, right? But remember, you're going from, so 14, you're going to 18, right? So this is 18 feet. So there's a 4 feet difference here. From this point to the center of the beam, there's a 4 feet difference, right? And so now I need to cover that with the stirrups at least the minimum area of stirrups. But we don't have a minimum area of stirrups. What we have instead is the spacing that corresponds to the minimum area of stirrups. And that spacing is 28 inches. So, from that point that we just found to the center of the beam, I need to add some stirrups that are spaced at 28 or less. Okay? Why? Because if I don't do that, I have to change my calculation of V sub C for that section, and I have to use the third equation that is in the ACI code, right? When you do not satisfy AB minimum. We don't want to do that. It's more work. So, no. So just pick some stirrups and satisfy AB minimum by the spacing. Okay? So I'm going to add 3 more stirrups, okay, to avoid that. And that will give me a cover of, I'm going to put in what? So we need to cover 45 inches extra. We are going to then do those 3 at 15 inches. Okay? And now 15 is less than the minimum spacing that corresponds to AB minimum, so that we also can do 2 stirrups at half points. You don't have to specify 22.5. You simply say 2 stirrups at the middle point and at the center line. Okay, and that's it. And you take care of that. Right? But you have to put these stirrups to satisfy AB minimum. Okay. Okay. All right. So then you plot your diagram versus what is needed, right? Versus what you are providing. So what are you providing? Well, I'm providing stirrups at 9 inches. Well, stirrups at 9 inches, that gives me 109, right? 0.1. For how long? Past the drop. Okay. So I'm providing that amount of strength right past the drop. And at that moment, right, I have stirrups, but I put them all just because to satisfy minimum. So really here I'm saying the concrete controls. So this is just only the concrete. Okay? Because the only thing I did is put minimums just to make sure I'm using the right formula. Okay? But this is what you're providing, okay? And this is what you need. Okay? In there. And you want to plot the stirrups. I mean, you can show them like this, and you will have them. So then it goes there, and then you add whatever you need as stirrups, right? As you need to satisfy AV minimum. So that should be AV minimum, right? Based on spacing. So in our case, we're putting 3. Really, we're putting not like this. We're putting one right in here, right in the middle, right? And then we're putting two more right here, right? And that gives us the 3. Or you can say, if within this distance, I'm going to put 1 at the middle and then 1 at the end. That's it. That distance also satisfies minimum requirements. So that's that example. 9.5, the only difference here is this word, right? Sand, lightweight concrete. Okay? How are we going to use that? That's all. The rest is the same. So again, you got your dimensions given, you got your L here from the face of the supports already. You don't have to worry about finding the value. I already explained how to do it. You have a bearing. Okay. And so we find our loads, right? Now we multiply by the weight of the lightweight concrete that we given. And so we got our loads. And then we find our shear, plot our diagram. Find our value at the distance D. The D is 17 inches. So we use the formula. WUD minus omega UD divided by 12. Right? And so that would be our formula. With that, you go and find your phi b sub c. The only difference in this equation, well, wait a minute. You said there is an NU. I didn't pick up that one. So this example has an axial load. Oh, yes. You have an axial load. Right? There. Oh, so the example has an axial. So you have two things in this one: lightweight concrete and axial load. Now, lightweight concrete is easy to deal with. And axial load is not too bad, but you're going to see a couple of differences now on what we've been doing. Now, why do I say plastic centroid? Remember, I kind of brushed this thing over a little bit. I mentioned what a plastic centroid is. And this is what you get, is the location where you apply your load, you will produce a uniform stress, right? And so in the case of a rectangular section, it's right at the center of gravity, at the center of that figure. So that's why we put that load, so we don't create any differences in the stresses. So that's applied there. And so you had your axial load, and so when I got my formula for B sub C, now has that axial load in there. Okay? We need to factor the axial load, so we did that. And we had to use a lambda of 0.85, which corresponds to sand lightweight concrete. Okay? And I already explained what sand lightweight concrete is and all lightweight concrete is, right? So don't be surprised if that comes in one of those part A's, right? All right, so we put the formula here, we substitute our numbers. Remember, this is factor load, and U, meaning factor load. And I get my value, 1688. So to find this value, which we've been finding in the previous examples, right? What we did in the previous examples is we took the phi b sub c and divide by 2, right? And we got the number. Well, now we cannot do that. We cannot do that because we have an axial load effect. So half of this is not this anymore. All right? So we had to find the value. Now it happens to be pretty close, but that depends on what load you got here, right? So if I had a higher load, that will not be the case. Right? This one will remain the same. This one will be a lot higher. Right? And so now you can see I cannot do half. I had to actually find the value. So that's the two differences. One, we're adding the lightweight coefficient. That needs to now is not 1. Second, we add a factor load. Okay, so we need to properly factor depending on the type of load. And then we learn that in this case, when we use this formula with an axial load, we cannot take half of that to get this one because it's not, right? And so we actually have to find it. Okay? So that's it. That's the only thing. The rest is going to be the same. So how do I find my length of stirrups? We can do it by proportions. Mm-hmm. and this is correct, because in this case the z value, this is the difference. The z value is measured from here, and the x is going to be measured from here. And so when we do the proportions between the large triangle and the small triangle, right, we get the z value, and from there we subtract it from 132, and we get the length that needs to be covered by stirrups. And then the same, we find this phi v sub s by taking vu at d minus the concrete strength, check against the two formulas. It is below the first one, so d over 2 and 24 controls, check for minimums, right? And we got 22 is your minimum spacing. So, I mean, not the minimum spacing, it's the spacing that corresponds to AV minimum, okay? 22. But 8.5 is going to control at all throughout the beam, right? And this example we already did, that was kind of the first example that we did, but you got the same value controlling throughout the whole beam. Across, well, since your beam is only 12 inches wide, and this allows you to have up to 17 inches between legs, you're satisfying that, right? Next, you find your S required. Right? That's 11.4 is more than the 8.5, so you cannot use that number. You have to go with 8.5. Now, that runs down to 8 inches. We do 8 inches. And notice that he did here 1 and 2, 13 and 8, that gives me 106, always more than what is needed, right? And then I added 2 more stirrups, right, at equal spaces to the center of the beam to cover my minimum requirements, right? I need to cover 26 inches, so that means if I'm using 2 stirrups, I'm putting each at 13 inches, and that's less than the minimum space, is less than the spacing needed for AV minimum. Okay? So don't forget, that's that one right here. So that's the spacing needed to satisfy minimum shear requirements. Right. So we get that one. So that's pretty similar to the other. Okay. Yeah, let me do one more example. 9.6. 9.6 is special in the sense that now you're going to deal with a cantilever beam. So what is going to change? Well, first of all, you're going to see that the calculations itself on how to find the shear and the distance d and v sub s and all that, no changes there, okay? So we start here, find the beam weight, find our load combinations, load our beam, find our shear diagram, all that is the same. Find my shear, that will be my shear at the support, right? And then you find it at the distance d, using the same formula, it will be VU at d minus the load times d, right? So because there is no other load here, so we're good. So be careful, because sometimes the formulas in the beam formulas, they may give you the shear at the distance from this tip. So that's different than the shear calculated from this point. Okay? And so be careful. Okay? So we do it from this side right here, and there is no other load applied here, only uniform load, your formula, the formula that we have been using remains the same. Okay? In terms of what we need to find values. Now you can always do the proportions, but now in order to have the triangles, right, I need to do 137.2 minus 16, that gives me the height of the triangle, and then the length, which is 144. And then I have 18.3 minus the 16 will give me the height of the triangle, little triangle here, divided by my z value. So now that z value is 2.7. So 144 minus 2.7 gives me 141.3. Really what this is telling me is basically I need to cover the whole length of the beam with stirrups, right? Indeed. You can use your formula. I mean, you can use your formula for shear, right? And you will have the same as this formula, right? Your value at the face, 137.2 minus WX, right? Should be equal to 18.3. And you solve for X. So X measured from there. Right? And that gives you length of stirrups too. So you can use that formula or you can use proportions, either one. You don't have to do both, okay? In the examples, sometimes I show you both, so that way you can pick whenever you want, but you don't have to do both. Okay? There are cases where you may have to do these proportions because all you're given is the figure of the shear and not the loads, so then you don't know what to do that, especially in the FE exam. Okay? In the FE exam, they may give you the shear diagram, but not the loads. So then you have to use proportions. Okay? So I find my phi v sub s, same as before. The value of D minus the concrete strength, the difference is the steel. Remove the phi factor, check my ranges. And here my range went past the 4, but less than the 8. So that adds one complication here. So now my maximum spacing within the distance D, right, is D over 4 and 12. And that becomes 5.9. That's my maximum within the distance D. Okay? So this is valid as long as our shear, right, is higher, right? Our shear is higher than this value plus the concrete strength, right? And if we add a little bit of concrete strength here, 97.6, and we add that to the, so the 97.6, we add it to the concrete strength, we get 109.8. So then that spacing will have to be valid as long as we shear is higher than this number. Right? But as you can see in the diagram, it's going down. So eventually it's going down to 16, right? So some point around here, when it's pretty low, right, I have to use, in the design aids, right, I will have to use the first column. Okay? So let me get, if I can get it, that one, there it is. So there's one right here, there it is, right? So I'm going to use then this value. Eventually we're going to get here, right? Because there the diagram is going down, right? So at one point it's going to be right between these two numbers. And so we need all these formulas. So we need that one and we need this one. Okay? We have been using the last box here, right? But we're also going to need that eventually, and we're going to need the minimum requirements, right? There. Okay. All right. So we go here then, and we find also the spacings for those cases. Okay? So to satisfy AV minimum out of these two, I had to have 30 inches. I cannot exceed that. Okay. To this value of 11, it starts working after we pass this number. So that's the number we calculated here, right? Which is your steel and concrete. Right? And this is a simplification, really, because we have an axial load? No, we don't. So that's good. So there is no axial load, so we can do that. Okay? Otherwise, you have to include the axial load. But we don't. So we add these two. And so that's 109.8. So at the moment we go below that, I don't need to use this spacing anymore. Okay? because now my V sub s is going to be below 4, and that means I have to use d over 2 or 24, and which is already here, which is 11. So that means that after that point, I will have to use a maximum value of 11 inches. Across the width, again, the width is only 14, and the core allows all the way to 23.5. We're good, right? Okay. Now we find the required spacing, and so we have our area of steel, 2 legs. And I don't know if I mentioned this, but that's typical. For a beam, you're going to have a minimum of 2 vertical legs. That's the minimum you're going to have for beams. We're using number 4 stirrups, so that's 2 legs of number 4 stirrups, 60 and then 23.5. My V sub s is 5.2. That's less than the maximum by a little bit. So what that means is I have to use 5 inches. I have to begin with 5 inches. Okay. Next, I need a table. Right? I need a table to go from what? From 5 to what? To 11, right? Which is my maximum. Right? So I need a table to do that. So there it is. I need 5, 6, 8, 10, 11. Right? So that's there. And again, I mean, we create the formula here as a function of s. That will give us phi v sub s for each of these numbers. Right? And then we add to these numbers, we add the concrete, and we get the design strength. Right? This value now, let's see, am I using Z or X here? Make sure that we get the right value. It says X. Okay, so here it says X. Right? The Z is this one. So from the face of the support, this is X. Okay, so that is X. I thought I had changed all these formulas. Maybe not. Okay, so all these are X's. So because we're doing it from the face of the support. Yeah, there's the X doing proportions. Or using, so you can use, again, you can use your proportion using similar triangles, or you can use your formulas for shear, right? And here the formula includes the PU value, okay? And so it tells you what the value of the shear is. Okay? And so those are the formulas. All right, so that means you calculate then where 121 happens. It happens at this distance. 107 happens at this distance. 89.5 happens at this distance, right? And so on. And so this tells you when you can switch. So here we're going to start then. Always 1 or 2 or 3, right? We have to start here. Then the next one has to be the 5. You have to use the 5. So again, you're not going to switch to 6. Okay, that's not a good idea. So I can switch to 8 or I can switch to 10. In this case, if possible, sometimes it's not. Since we're starting with 5, it would be good to go to 10. So that way, the guy in the field knows that you're doubling the space. He can see it visually. All right. So that's one way of doing this. So I do 1 and 2, 14 and 5, right? And then the 7 and 10, and that covered a distance of 142. And I needed to cover for my stirrups, right? We said almost to the end of the beam, right? That's what we said. L stirrups is practically the whole beam. Oh, but the whole beam is 144. So then I should go all the way to 144, right? No. Why? You need to have a cover distance, right? Cover distance. So in this case, it would be a 1.5 inch, right? That you have, and then half of the stirrup, because that's the first you want to hit the stirrup, right? So about, in this case, I mean, you were using number 4s, right? So that's like 0.25. So you have a minimum of 175 that you need to have there. So here I'm leaving a gap of 2 inches, yeah, to make sure that I have enough of the tip. So make sure that you don't go. This is very important. That's what this example is for. That you do not go past the 144. Okay, you cannot go past the number. You're gonna put a stirrup in the air, right? So make sure that you don't do that. You have to stop at least, I would say 2 inches. That's a good distance. So that would be your last stirrup at 2 inches, maybe 3 inches. Okay, we can do that. Maybe 4. Okay, 4. I'll take it. All right, you can do that. But that's what you have to have it. Okay, but no, do not go over, because it doesn't make sense. Okay. All right. So that's important for that one. So we do that. Then here it shows you the different types of combinations. There is not just one solution. But notice the jumps, okay? 5, 8, 8, 11. Okay? 5, 8, 8, 10. I don't like that one much, but that's okay. Okay? So there are different kinds. So there it is. 1 and 2, 14 and 5, 7 and 10. Okay? So the first one kind of my preferred choice. And then you want to plot the required strength versus the actual diagram. So what is your required strength? Well, you're using 5. That strength is 121. And for how long are you using that? For 70 plus 2, 72 inches. So for a length of 72 inches, you're going to use this. After that, you are going to do what? You're going to do 7 at 10. Okay, 10 gives me 78.9. So after that, I'm providing 78.9. And that takes me pretty much to the end of the beam, right? And so that's what I'm providing. Okay? So that's how you plot this provided line. Okay? This is the shear strength provided. Okay. I think it would be more useful if I do 913 at this point, because you're doing your project, and 913 covers joist. Okay. So let's do the 913. I mean, you've probably done this, but hey. So here is a joist, right? We find for the joist the moments and the shears using the coefficients. We've done that already. And so we plot, right? Notice that my plot looks like this, right? And when I put it here, I kind of flip this diagram, right? It doesn't matter. I mean, you don't have, I mean, you like to put it this way and work that way and work from right to left. Well, that's okay. I mean, you can do that. But all I did is took the diagram and just flip it, okay? And work with that. No? All right? So that's kind of what we're doing, in there. All right. So we have our values, our shears, 16.7, the value of the distance D. Again, reaction minus load times D divided by 12. So we got our numbers there. Okay. And again, we're going to find the length that needs to be covered by steer. So we find our phi sub c that you can do. Now, because this is a Y module joist, skip joist, right? You are not allowed to use the extra 10%. Okay? So we have to use the regular formula, no 10% increase. That is that number, right? Because we're using this equation and there is no axial load, then this value happens to be half. right? So half of that is this. The V sub C without the phi factor, we just divide it, we get that now. VU exceeds the 10.3, which is that one, so stirrups are required from the face of the support to wherever this number happens. Where this number happens? Oh, just go to the equation for shear, replace the VU with 10.3, and solve for X. So notice that everything is the same. No difference here, okay? I need to cover 77 inches of that. Eventually, eventually your diagram goes down and goes between V sub C and half of V sub C. And so right here you will have to check for minimums, and so that will be the first column of the table. So here you have to use the second column of the table in the design aids. Here you had to use the first column in the table of the design aids. So we had to calculate all those values. Okay? And so I did that here. Remember that out of these two, the lowest value controls your AV minimum spacing. Okay? So 13.6 is the spacing to satisfy minimum values, but to satisfy my design is 9 inches. Okay? So 9 inches is the spacing I have to use to satisfy my design. Okay? Next, I find me some kind of V average here for my width, right? Because remember, this is trapezoidal, right? So we're going to find a V average that we can use to help us a little bit on the shear. Okay, so that's then my B average. Okay, and now I'm going to use number 3 stirrups, 1 and 2, and 9 and 9, and again that covers a length of 83, which is greater than 77. Right? For construction purposes, I need to put more stirrups, right, such that the spacing of 13 inches, which is the spacing corresponding to AV minimum, is satisfied. And that's pretty much it. So in skip joist, you have to treat it like a regular beam. There is no 10% increase. You can use a B average instead of the B at the bottom. That will increase also your B for the calculations, which is good, right? And that's all. Okay, so I'm going to stop here for this part, and